So Dr. Oza, I have known Dr. Oza for a long time. We both did our PhDs together at UC Berkeley. He has that since then he joined NASA. He has been with NASA for quite some time. He has done some truly impressive projects. He has more than 50 research publications. So he has won so many awards that I don't think I can list them all, but I'm going to pick a few. So in 2019, he was named as one of the 50 key people in the United States government working to move adoption of AI forward across the industry. So, which is, I think, a really, really impressive thing. He leads a number of data science teams at NASA Ames, and he will be speaking with you guys about the work that his teams are doing. He has won many awards. He's co-authored one of the 5 most innovative technical papers in the SAE community, and his teams have won a lot of awards. He has a bachelor's degree in mathematics and computer science from MIT, a master's after that, and then a PhD in computer science from UC Berkeley. So welcome, Dr. Oza. Nikunj, would you like to share screen? I think sharing screen permissions are available.
Yeah, please shout through the chat if something goes wrong. Thank you. Thanks so much, Dr. Talagala, for inviting me to this, and to all of you for putting up with me here for this keynote. So I'll talk about data sciences at NASA. I mean, as you might expect, actually NASA does use AI generally a fair amount. So we have everything from robotics for, say, things like Mars rover, to automated planning and scheduling for Earth observing and space observing instruments, so that all different scientists can put in their requests for observations, and then the planning and scheduling system will mediate among all of them and try and satisfy everybody's observations in the best way possible by using an automated algorithm for it. But of course, since I lead a data sciences group at NASA, I'm going to skew things towards data science. So if you could go to the next. So if we were allowed to sponsor T-shirts, I would probably put maybe a more creative version of what you see in red there. But essentially, the group does machine learning and data mining research and development for application to the full range of NASA problems. So people probably most often when they think of NASA, they think of human space exploration, and they may also think of space science, things like the search for Earth-like planets using instruments like Kepler and TESS. But NASA also happens to be the U.S. research agency in charge of aeronautics. So this includes commercial aviation, so the sorts of aircraft you all might take to travel around the country and around the world, but also UAVs. So there's been discussion, of course, about UAVs for things like package delivery and maybe eventually taxi services, but already they are used for things like monitoring for pollution, or let's say after a disaster, scoping out the area and assessing what is the best way.
And Nikunj, the audio breaking up a little bit again. Did something change?
But I hope not.
Okay.
Other than the phone system not liking Earth science, why don't I just try switching to the computer audio just to see what happens?
Sure.
Okay, hang on. Okay, how is this?
So much better.
Oh, wow. I'll make a mental note of that. Okay. Okay, yes. Thanks for bringing that up there. So really we're looking at machine learning and data mining for the full range of problems. And Nisha in her introductory talk here was quite prescient, actually, that it isn't really entirely about AI. I mean, in a way, you could argue that NASA does not directly care about AI, right? They care about these problems: aeronautics, earth science, space exploration, space science, and will use whatever tools that are available to help solve these problems. And so the reason we care about AI and data sciences is because, to a great extent, what Nisha alluded to, there are large data sets. There's also some more difficulties with that. Often the data are noisy, and there are other problems that I will get into a little bit later. But in the net, we feel like these will actually help improve our solutions to these different problems, where improve could mean that it's faster, more accurate, is cheaper in some way, removes grunt work so that essentially we can all be doing more useful things, etc. Now, the data sciences group here, you can see that we are 12 people right now within the group. And we do often have students. We have had high school students, for example. So, please do keep in touch if you're interested in interning with us. And the range of backgrounds of the members of the group is quite varied. So there are people like me and Hamid that you see listed here who actually do have a machine learning background. And so in our case, we do have PhDs in machine learning. But there are others who have different backgrounds. So we have people like Ilya, whose background is very strong in mathematics. People like Thomas, he actually got a PhD in experimental psychology and then actually moved on into engineering. And so he has a very strong engineering background. And then he learned about data science. And we have had people in the past who have, let's say, done a PhD in mechanical engineering, but as part of that, they saw the importance of data and data science, and they kind of got bitten by that machine learning data science bug and then decided to join us. But having that additional background in engineering or let's say earth science, or whatever it may be, that helps them very much at NASA because they really understand both the tool side, the machine learning and NASA side, but they can more easily understand the domain as well. So if you could go to the next. Oh, and one quick thing I should actually answer is that many people do assume that in order to be at NASA, you need to be a U.S. citizen. That actually is not the case. If you want to be a direct government employee like me, yes, you do have to be a U.S. citizen, but we also do have contractors where the person officially works for some different company or university, but then NASA has a contract with them, and so then they're able to still work on our site. So now, Nisha alluded to a great extent to this in what she spoke about, but essentially what we're trying to do in data science is understand the operation of some kind of a system. So in case of aeronautics, it could be a single commercial aircraft, it could be an airport with a bunch of aircraft trying to take off and land around it. It could be the International Space Station, or in case of something like Earth science, it could be the entire Earth, or let's say the Greenland, if you're interested in studying things like the Greenland ice sheet and how it's melting and reconstituting and the like. Now, these different systems operate in some kind of environment. We have varying levels of understanding about how that system operates in different environments, but a good way to really try and understand things, how the real world works, so to speak, is by looking at data from the operations of these systems. So, for example, for Earth science, we have satellites, we have airborne instruments, ground-based instruments that take all sorts of measurements. We can put all those together and learn something about how the Earth is actually working. And now if you think about it, we do the same kind of thing quite often, right? We just yesterday, my dad was complaining that normally when you make a phone call using something like WhatsApp, you actually have to tap on who you want to call and, push this certain button and then it starts ringing. Well, he said it just started ringing. He hadn't touched the phone at all. So that's a case where you see a certain sequence of data points and think, hey, that's a little bit funny. And now we might do the same kind of thing, right? You ask your parents that you want to have a party at home. Normally they'll say no and get upset, and you might enjoy watching them get upset that way. But let's suppose suddenly your parents say, oh, okay, yeah, you can have a party. You're not just going to get excited, right? You're going to think, hey, wait, something's seriously wrong here. So we do this kind of data science every now and then, and what we're talking about here is just doing this on a more formal basis. So if you could advance to the next. And it's probably not super vital, but the left thing is a video there. So if you could, I think you may be able to click that and, or maybe not.
Do you want me to try to play it?
If you could, or did it not get sent?
Oh. It looks like it's not a link, so.
Oh, yeah, that's all right. Then I could kind of describe it. So within aeronautics, so what the left video is meant to depict is, so this aircraft is flying along, but then it experiences what is called stall. So essentially with stall, the aircraft is going too slow for the wings to be able to generate lift. And so then the aircraft just falls. So in this case, actually, the aircraft continues going up a bit, and then it'll actually kind of bank to the right. And then the video stops as it's about of that white van that you see, but kind of further ahead. So in the context of aeronautics, of course, knowing that the aircraft crashed in that case isn't really helpful. Everybody can see that. What we're interested in is what happened right before that. So we know about stall, where, okay, the aircraft didn't generate enough lift, but what caused the aircraft to go into stall in the first place? Was it, let's say, was the aircraft about slowing down, but somehow the pilots were distracted with something? Did something go wrong on board? Did something with the autopilot go bonkers? Where maybe did it think it was going fast? The aircraft think it was going faster than it really was. Right? There are many different possible causes, and also there is a notion that we don't want to just say that we are either safe or not safe. There is a notion of how close we are to being unsafe. And, we see that on the road all the time, right? We've probably, when driving, sorry, many of you in the audience, haven't been able to drive yet, but all in the fullness of time, we have had close calls, right? Where, okay, a crash didn't happen, but we got close. Now, we don't want to get complacent, right? We want to, in that case, figure out, okay, why did even that close call happen? So that's a lot of what we try to do here, try to find what are those data that represent something that's kind of unusual. And then looking at those unusual data, found, let's say, using some kind of anomaly detection method, then get a domain expert to look at that and determine, is that something that's actually of safety relevance, or is it some kind of a data glitch, or is it actually something that is allowed? Like maybe an aircraft took an unusual trajectory, but maybe the air traffic controller directed him to take an unusual trajectory because of a problem with some other aircraft, let's say, that was already on a certain runway. And so then the aircraft was told, okay, direct it to another runway. We're trying to find individual anomalies like that. And we're also trying to find the conditions under which those anomalies are more likely to happen. Essentially, kind of like what I described in an earlier slide, what is the environment under which an anomaly is more likely to happen? Or what is some other kind of a condition where by itself it may not be dangerous, but for whatever reason, that's a circumstance under which you're more likely to have an anomaly happen. We're looking for those kinds of things as well. There is also an aviation safety reporting system that is run out of NASA, where after any commercial flight, anybody, pilots, flight crew, even passengers, can submit a report if any kind of safety issue happens. We do look at those reports. and try to determine, okay, what is the nature of the safety issue? How might that show up in other objective data like radar track data, data from onboard the aircraft, and the like? And maybe the report could guide us to something that we may have missed in the data. If you could go to the next. So in earth science, to some extent I described this, but we do have, as what is depicted on the left here, quite a range of earth observing instruments. NASA is biased somewhat towards remote sensing, so these are space-based instruments, but we do also have a fair number of airborne instruments, and we do make use of ground-based measurements as well. So taking those observations, putting them together, assimilating them, which means using them to seed complex mathematical models, and also maybe machine learning based models, and then based on those observations, looking at what are, let's say, areas of the Earth or environmental conditions under which we still have high uncertainty, for which we would want to make future observations. So then the results of our analyses would lead to tasking the different observing assets. They would take new observations. We would assimilate them, analyze them, and then make more observation requests. And they can range they involve the full range of earth science problems. So certainly we've heard a lot about climate change in the press, but also we're trying to improve weather forecasting. We want to monitor any kind of severe weather phenomena like hurricanes, and take observations of areas that have been impacted by such disasters, and then use the data to plan how we would actually respond to them. So like, let's say if there are areas where there are people who are stranded, what is the best route to take and what are the best vehicles to use to be able to go and rescue those people? And then there are things like water resources. So we actually have satellite-based instruments that can actually measure underground water. And so we want to monitor those. So, what are areas that we can tap? What are areas of underground water that are starting to run low? So it really covers a pretty wide range of earth science problems and downstream what are called applications, even the sort of things that first responders may be interested in. If you could go to the next. So we also do have an interest in space science. So what's depicted here is effort by the Kepler and the TESS missions to try and find Earth-like planets wherever they may be. And one technique that is used is depicted here on the left, where you look at the brightness of some known star. In this case, it's this large, what looks like a sun here. And then we monitor the brightness and notice points at which that brightness dips. Now, what's shown on the left is quite exaggerated. That would be very easy to find. The data really looks more like what you see on the right, where just looking at it, it's very difficult to tell where there's enough of a dip in the brightness to be able to say, okay, yeah, there probably is an Earth-like planet here. Also, you may notice individual dips, but they may not be as periodic as what is depicted here, because you may have multiple stars that are, say, moving in front of each other. So you have to figure out is it that, let's say, there are two stars where one is moving in front of the other, and so what you're seeing is a dip in the two different stars at different times, or is it really something like this where it's just one previously unknown possible planet that you're looking for? And so if you could move to the next. Oh, so I should say one thing though. We did, two members of my group were involved in this effort, and in a recently published paper using some deep learning based methods, 301 previously unknown planet candidates were identified. And if you could move to the next. And so now this is within the area of human space exploration. So there are many systems that are involved in human space exploration, such as we have on board the International Space Station, we have various systems for things like climate control. And so this is one particular system where there was an ammonia bubble. I believe it was in some portion of the climate control system within the International Space Station. And in looking at the data, this was after the fact, unfortunately, they looked at it, and an online clustering algorithm that someone in our group developed, it turns out would have noticed a problem about 6 days before standard techniques ended up revealing this problem. And so, in fact, we do have this algorithm IMS running on board the International Space Station right now, continually monitoring, looking for anything unusual like this. And as you might imagine, it does help to have this additional lead time to be able to investigate problems and maybe mitigate them before they get worse. So if you could move to the next. So I'll go a little bit more into what we're doing for commercial aviation, mainly because I have been leading a machine learning team in this area for quite a while. What we're trying to do here overall is risk assessment for what is called the terminal area. So this means around a given airport, takeoffs and landings overall within flights tend to be the most difficult parts, where there are the greatest number of anomalies. So there's pretty good interest in that. So we are developing tools to collect and analyze data that is relevant and identify possible safety incidents. And we want to integrate these different tools into some kind of a dashboard. So loosely along the lines of what you see in the left 2/3 of the figure below. So this is bringing together various data sets from, let's say, onboard the aircraft or from around the airport, and then even at higher levels, like at the level of a full sector that may include many airports, trying to bring those data together. And then along the lines of what I described before, look for anomalies, look for any kind of precursors to those anomalies, anything that may represent something like a leading indicator, give some sort of a prediction where you say, okay, if you keep going at this rate, you are likely to have some kind of more significant problem within a certain amount of time, therefore give some sort of alert. And then we have not been as much involved in this, but mostly there will be some kind of mitigation response that is taken. And once the mitigation is done, of course, that is going to impact the data that we observe in the future. So then we would want to see, okay, did those mitigations really help? Did they help with what they were intended to help? Did those mitigations maybe bring out additional problems, actually, that may be unexpected? So with this is the full range of what we're interested in here. If you could move to the next. So this is just a depiction of the kinds of incidents we're interested in looking for. So the vast majority of the time, the aviation system operates in a safe state. So trying to find safety incidents really is very much like trying to find that needle in a haystack, like what you've probably heard about. So most of the time we're operating in a safe state, but then maybe under some kind of a context, which by itself is safe, you end up going into a compromised state. And for all of these transitions, the probability may be very low. So almost all the time you may be in a safe state, and suddenly there's like a 1 in 10,000 chance that you end up in a compromised state. But that 1 in 10,000 is much higher than it typically is. So then that's a situation where you want to say, okay, we're in a compromised state. Why? What's going on here? Now, most of the time, even from the compromised state, the system will return back into a safe state. But every once in a while, it may go into what I'm depicting here as an anomalous state. Again, there's a pretty good chance that the system will correct itself and go into a safe state. But there's always a small chance that you could get an accident happening, where in that case it could be, loss of life, loss of aircraft, loss of surrounding property, or all of them. And so we're really interested in finding that full sequence of what's depicted here as context, behavior, and outcome. And many of those are there's very low probability, as I mentioned, of degradation, but we're still interested in finding them. If you could go to the next. Now, the types of data that we deal with here are quite varied. So flight operations quality assurance, or FOQA, that is the term used for data that are recorded on board the aircraft. So there is, of course, the well-known black box data, but there are other data as well. Then there are also trajectory or radar track data. So around an airport, you may have seen radar tracks where each aircraft is represented by a dot and maybe by some sort of a description like a call sign. And then you see the, say, aircraft that are landing or taking off, or in some cases, aircraft that may be just passing nearby, moving around on this screen. So we do look at radar track data as well. I described a little bit about the safety reports. As you might imagine, weather has a pretty significant impact. There is also work on trying to use audio. So this is when air traffic control communicates with the aircraft flight crew. So trying to work with them either as audio or transcribing them and using the text, and even integrating those together with data so that you can see maybe when somebody spoke up, either let's say before or after we ended up in some kind of a compromised state. And then there's interest in using other data as well, like maintenance data. You can even imagine using things like pilot training records, any kind of changes in how the airspace is managed, information related to that, and there could be others as well. If you could go to the next. Now, the way I've described things so far, it sounds pretty simple, right? You just take all these different data, find some kind of algorithm, run it and get your great insights, but it's not so easy as that. Many of you have probably heard about the 4 V's of big data. One little bit of trivia is that the phrase big data was actually devised at NASA Ames Research Center in the Mountain View area. In a sister division, there was a paper written back in 1997 where 2 scientists spoke about using data that are too big to fit on their laptop computer. And so what you have to do to be able to actually make use of such data. So now actually, if you click thing that should show something more. So of course, one V of big data is the volume. So certainly let's say by Earth science standards, this isn't very large, but it's enough that you have to think about it. So say radar tracks from the 47 different facilities, you're talking about in an uncompressed form where you can really use it, you're talking about several terabytes per year of just for the radar tracks. And then you have weather and forecast data of a few terabytes as well. You can get into the terabyte range for multiple aircraft and their flight recorded data. So it starts adding up. So if you advance some more. Yeah, one more click, I think. Okay, yeah, you can just go one more, I think. Yeah, there was actually something, an animation that was supposed to come down from that pipe there, so essentially depicting the problems of volume and velocity and such things. But anyway, that's all right. So in addition to the high volume, there's of course velocity. So the national airspace is operating all the time, so the rate at which data are coming are pretty high. And then veracity is an issue. So these data aren't just always clean, smooth radar tracks or time series from on board the aircraft. You have data dropouts, you have duplicate tracks, so what looks like 2 aircraft that are flying right on top of each other, but they're actually the same one. You have flights that actually both start and end seemingly in midair. And then we have reused flight identifiers. So essentially the same identifier, but for two flights that are in very different places. So sometimes we've gotten some funny insight that, yeah, here's a flight that's very anomalous. And well, it is anomalous because it violated the laws of physics. And that's because these are for two very different flights. And then we have quite a variety of data as well. So there's the you have numerical and you have data that's continuous. You also have discrete data. Then for weather data, the data that you get is actual, but in some cases you're actually working based on forecast data, or at least say if you look at let's say an data from let's say a month ago, they may have been relying on forecasts to make some of those decisions. So you have to know the forecasts from back then to perhaps justify the decisions that they made before. And then I've made mention of voice data, where in some cases that may be transcribed into text, but sometimes you're dealing with it actually as an audio. And then you have text reports. You may have multiple reports on the same incident, but from different perspectives. So then you have to reconcile those. So there's a substantial data challenge that you have to deal with as part of this. If you could go to the next. So I'll describe a little bit actually, primarily of anomaly detection. I won't describe so much of precursor identification, but within text mining, I'll only briefly describe that we have had two main problems we've been working on. So one is classification. So this is given some kind of a narrative, classifying the report into the nature of the problem that is being discussed. So like, is it, let's say, is the problem being described like a runway incursion, or some kind of miscommunication with tower, whatnot. There's a set of classes that are typically used, and then there's also topic identification. So this is using something like latent Dirichlet allocation to look at a whole repository of reports and see what seem to be the different types of problems that are being described. So you have multiple vectors of words where the words may somehow be related to each other, and so that can tell you what kind of problem is maybe being described. So, for example, one topic that we found looking at a fairly large repository of reports involved words like fatigue, late, night, sleep. So then you can imagine this is probably reports from pilots complaining about, having, let's say, had a delayed flight, then they had an early morning flight the next day, they were very fatigued, got very little sleep, etc. So if you could go to the next. So as you might expect, the aviation industry and FAA and others are already looking for safety issues, but the way they do it primarily is through what are called exceedance-based methods. Essentially, these are rules, kind of like what's shown in the second bullet there. So let's say during landing, when altitude is 1,000 feet, if the speed is greater than 250 nautical miles per hour, that is what is called a high-speed exceedance. So of course, when you define something like this problem, you can very easily identify it. So these exceedance-based methods are pretty good at identifying known anomalies, but almost by definition, they cannot identify unknown anomalies. So that's why if you go to the next slide, there is interest in kind of flipping the problem on its head, as it were, by kind of letting the data speak for themselves. So discovering anomalies by essentially learning the statistical properties of the data and finding which data points kind of don't fit, right? They're kind of far away from most of the data points or of low probability. And of course, these methods are complementary to the existing ones in the sense that they have a relatively low false negative rate. We figure that they do because, of course, as we mentioned, the aviation system, it's very safe, right? The accidents, incidents, injuries, and certainly deaths are very rare. So we can safely assume that pretty much all of what is statistically normal, whatever the methods claim are normal, they actually are operationally normal. Among what algorithms, data science algorithms find are statistically anomalous. There may be some that are like false alarms where it turns out there's actually no safety issue there. And then there are going to be some that are known problems. But we want to find what's depicted here as the unknown problems, which are the ones that the rule-based methods don't find, but somehow over time through the operation of the system, these problems have started to pop up where a safety analyst would say, okay, yeah, this is of concern. There is a greater probability than normal of having some kind of an accident or injuries, whatever it may be, and therefore we want to find some kind of mitigation. And we have had some history of doing this with airline partners where we use a data-driven method. Yes, there will be some false alarms, and we move past those, but we do find some useful insights, some previously unknown problems that actually are safety issues, and those led to the modification of the exceedance detection methods that are used. So additional rules are devised to go into the exceedance-based system to now start looking for these additional problems that our algorithms identified. So if you could go to the next. Oh, okay, yeah, this is kind of what I went into about that we're interested especially in finding these previously unknown problems, and looking for statistically anomalous data are a good way to do that. So if you could go to the next. So this is an example of the type of problem that, in fact, we found. So this was an aircraft where about 30 seconds after takeoff, suddenly the airspeed started to just drop. Now, normally, speed is supposed to go up as you're increasing in altitude. And in this particular case, the aircraft dropped to only 12 knots above the estimated stall speed. And so that's why our algorithm put that very high on the anomaly list. And we did not give the algorithm any kind of indication that, okay, typically, during takeoff, altitude should go up and airspeed should also go up. We just gave it a lot of data, and then the algorithm was able to find that, okay, this is unusual. And certainly there was this notion that, okay, yeah, you don't want airspeed to go down as altitude goes up, but it turns out for this particular flight, they didn't realize how close it actually got to stall speed until we showed this particular result. If you could go to the next. So what I showed before was an anomaly in continuous data. There's also can be anomalies in the discrete data, in this case, between autopilot modes. So this is a particular anomaly we also found where it turns out somehow the pilot and the autopilot had different impressions of what autopilot mode should be used, and so the pilot and the autopilot started fighting over it. So they kept you ended up seeing this back and forth switching between two different modes, and eventually the pilot got fed up and just decided to actually recycle the flight director, equivalent to kind of rebooting the autopilot, kind of like what many of us do with our laptops, I guess. Although doing this in an aircraft that is operating at least sounds a little bit more concerning, but don't worry, nothing really bad happened. But this is a case where we've found an anomaly in the discrete data. So if you could go to the next. And then this one, yeah, I don't know if it'll play. There's actually supposed to be a video as part of this, but oh, maybe there isn't.
Let me try, hold on. It does not look that way. It looks like an image.
Oh, okay. Oh, heck.
No problem.
Yeah, life. So essentially, you may see that radar track there on the left. Essentially, it kind of went almost diagonally down to the bottom right corner, and then was supposed to take a left turn and then land on the bottom runway there, which it did do, but it actually overshot the bottom runway and came almost in line with the top runway, and it got close to another aircraft. And then it was able to get back on track, but generally they don't like the aircraft getting too close to one another. So anyway, sorry that this animation didn't show up, but in any case, yeah, this we can look at this. So, I described about how we have continuous and discrete data, and you can imagine other types of data as well. But how can you use all of them at the same time? So the way we are doing this is using kernel methods. So there's an area called multiple kernel learning that really it's probably started back in 2009 or so. And in our case, we're using that for anomaly detection. And the basic idea is this, kind of as I described a little bit earlier, we can assume that if a flight is very similar to most other flights, it probably represents normal operation. Whereas if a flight is very different from most other flights, it probably represents some kind of anomalous operation. But how do you actually measure, similarity when you have both discrete and continuous variables and they're on different scales? You may even have other data types. And so the way we do it is through kernels, and kernel functions essentially give some kind of a measure of similarity over a particular data domain. So let's say we have one kernel over discrete sequences, one kernel over continuous sequences, and then you can have other kernels. But the key is that all of those kernels will then give you a measure of similarity ranging from 0 to 1. So if essentially you have pretty much the same, you have two flights operating in pretty much the same way, the kernel will give you a value of 1 or close to 1. Whereas if two flights are very different, then you'll get a value close to 0. And so you can have these multiple kernels, and then if you just combine them by, let's say, averaging, you're averaging a bunch of numbers from 0 to 1, you will get another number that's from 0 to 1. And so that final kernel value, the average, will essentially tell you that for two flights across all of their modalities, discrete, continuous, and whatever, how similar are they? And so that's where we can get to answering the question that I described. Is a given flight very similar to most other flights or very different from other flights? And then we can use that to tell us, okay, how anomalous is a particular flight. And in this case, we were able to see whether a flight was anomalous just in terms of the discretes, along the lines of the autopilot problem I described before, or is it anomalous in terms of the continuous, or is it anomalous in terms of the relationship between the two? You can imagine the discrete and the continuous by themselves being normal, but they not really matching up. So we're able to find anomalies there as well. And so we, came up with these kernels appropriate for our aviation data, but we use off-the-shelf anomaly detection algorithm, in this case, one-class support vector machines, and we were able to use that for this problem. So if you could go to the next. And I should say, yeah, that MKAD is what identified the particular anomalies that I showed earlier. I won't go too much into this. This is, more for those who, enjoy looking at mathematics, and it just shows that I was actually able to put this formula up on a PowerPoint without making a total fool of myself. Key thing here is just really what's depicted here, that we have a discrete kernel, we have a continuous kernel. We did a little bit of experiment with adding a text kernel. You can have actually as many different kernels as you want. And as long as those different beta values add up to 1, you actually have a proper well-defined kernel, and you can use the same algorithm. And you can use the same algorithm regardless of what kind of kernels you have. So in fact, we were able to use the same underlying algorithm both for the kind of data I showed earlier. This is, flight operations quality assurance data recorded on board. We were able to use the same algorithm for radar track data, where of course we replace these kernels with kernels appropriate to latitude, longitude, distance to nearest aircraft, etc. So if you could go to the next. So I kind of alluded to the problem with these data-driven methods, which is a higher false positive rate. Probably the students don't remember the car alarms, but many of their parents probably do remember that car alarms at first were really great, but then it turned out there were so many false alarms, pretty much people ignored them. And you can have the same kind of problem here. Eventually, our anomaly detection algorithm can just be seen as something like a Chicken Little and be ignored all the time. So we figured we should have a good way of addressing this higher false positive rate, which I'll describe starting on the next slide. Oh, actually, if you could go forward some more. Oh, yeah, I could think you could actually, yeah, just back. Yeah, that'll be good enough. So, I already described about how the operationally normal we're not interested in. What we want, what we did essentially is find some kind of or develop a classifier where it says, okay, um, given anomalous, uh, let's say a data point is found to be statistically anomalous, classify it into whether is it actually an operationally anomalous problem, is it actually of operational significance, or basically is it a false alarm? And developing that classifier is what I describe on the next slide. And yeah, if you go forward, it's supposed to have an animation in it. I think it's a PowerPoint based one. Yeah. So the key thing though is that, or
Oh, sorry,
maybe it,
am I supposed to go one more step?
so because within that slide, there was supposed to be
Okay.
things shading and such things, but
I don't know what's going on. It may be a Google Slides issue because if it's PowerPoint animation, maybe it just doesn't show up in the Google Slides.
oh, that's true. Yeah, Microsoft and Google don't like each other very much, do they? So,
No, no. So,
oh, sorry about that. Well, so I'll kind of describe it. So, essentially, we want to get domain expert feedback, right? So when our anomaly detection algorithm identifies an anomaly, we want somebody who is trained like a pilot to be able to say, okay, is this actually operationally significant, or is this essentially a false alarm? But these domain experts aren't going to do this all day, right? We have a retired pilot who has sometimes worked with us, but he'd rather hang out with his grandson than hang out with us. So we can only bother him for a limited period of time. So we use what is called active learning. So this is an area of machine learning that respects the fact that actually getting labels is costly. And so it will try to find what is that example where if you could only label one example, which is the one you'd want to label? It's the one that's going to give you the biggest bang for the buck, the biggest reduction in the false alarm rate. And so what's depicted here is that we first are going to select some kind of a bootstrap sample. So, maybe a handful of samples to get at least an initial classifier. But then based on some kind of a measure, like maybe the classifier's confidence in whether a particular flight is anomalous or not, we will ask the domain expert to review, right? Like the classifier may say, okay, I'm not sure about this one. Can you go and review it and tell me, is it operationally significant or not? Once we get that annotator's label, we'll update the classifier and then again say, okay, hey, if you have the time, can you review this flight? And if he does, then update the classifier based on that. And so we ask the domain expert, like let's say a pilot, not only whether the example is operationally significant or not, but also what features he used to make that determination. And so actually, I think this is shown on the next slide. Um, we developed this, a pretty simple interface where, let's say, it'll show a particular flight, in this case, a bunch of these variables. We also show the 10th to 90th percentiles for the different variables just as a guide for the pilot. And then we allow the domain expert can choose which are the key features that he wants to review about the flight. And then what you see as text there is actually entered by the domain expert. So in this case, it's him saying, okay, yeah, this flight was high and fast. The flaps could not be deployed without overspeed, et cetera. And so then these different features, things like say altitude and airspeed, and one is the throttle input that the pilot gives. So we would then know, okay, those are going to be key features, and so those go into the classifier to help then improve it, assuming that those features haven't been used already. If you could go to the next. And so we did a test with one rather patient pilot, and he actually went ahead and labeled. In this case, I think there were a total of 98 different flights that we asked him to label, and we were able to show that through active learning, assuming he had only labeled like the first 46 of those flights, using the active learning, we would have found 4 additional safety relevant flights as compared to what our vanilla anomaly detection algorithm would have found. Now, 4 doesn't sound like a very large number, but keep in mind 4 candidate safety incidents means 4 potential safety issues, accidents, etc. So finding individual things like this can, in this particular domain, is pretty significant. So if you could go to the next. So this is just showing you another algorithm that we developed along this line. So kind of as I implied earlier, we tend to have limited labeled data, but we of course have lots of unlabeled data, lots of flights. So this is a good candidate for semi-supervised learning. So with semi-supervised, it's kind of the bottom left is a good way of depicting it. So the gray dots represent unlabeled data. And you can see that those gray dots give you a pretty good idea of the data distribution. And then for those few flights where there are labels, you can see those are different colors there, like red and green and yellow and blue. And you can see from that you can come up with, even with relatively few labeled data points, you can come up with a pretty good guess of what the labels for the gray data points should be. You would probably guess that the data would be labeled along the lines of what you see on the right there. So if a gray point is surrounded by yellow, chances are it's going to be yellow. So that's essentially what semi-supervised learning is exploiting here. And so we're taking these the numeric data that you see up above, and we're using neural network-based feature encoder to map the data into the space you see in the bottom left, and it's in that space that we actually are using the semi-supervised learning and using that as a way of essentially filling in guesses of what we think the labels are for the unlabeled data points. So if you could go to the next. So this is just showing a few results here where of taking some training data where, of course, the majority are nominal data, but we managed to find some cases where there was excessive speed during the approach, some where the path was too high, and then some where the flaps, which help in slowing down, they were deployed late during the approach. And then there was a separate test set used to actually evaluate the models. And then if you could go to the next. And so this is just, I won't go tremendously into the details of this, but essentially the key result is in text in the middle there, that essentially we were able to get much better accuracy using, let's say, only 100 labeled data points compared to a previous algorithm that we had developed that really is kind of a supervised learning approach that really does require a fair amount of data. But yeah, if you could go to the next. So I really described a lot in aviation. I'll just describe a little bit here, a problem in the area of human space exploration. So it turns out because of the low gravity environment that astronauts operate in, astronauts have a higher than normal probability of getting symptoms consistent with diabetic retinopathy. So this is a case where if you look at the images of the retina and the blood vessels there, the blood vessels become more dense, then they restore to their original density, then become dense again, and then oftentimes blindness will result. And so that's why NASA is interested in looking at astronaut retinal images and trying to essentially assess, are the astronauts on the path towards this retinopathy. And generally, there is vascular structure in other places as well, like plant leaves have a vascular structure to them that's important for plant growth. There are also other health, like gastrointestinal systems for which vascular structure is very important. And so there is this software called VESGEN that is able to take images of vascular structure, kind of like what you see at the top right, and tries to turn them into what you see below, which are clearer images. Things like, let's say, the red and green, what you see there, distinguish the arteries and veins. However, processing a single image like what you see at the top typically takes anywhere from 2 to 25 hours per image for a scientist. So that's one place where we feel like machine learning could get much faster results. So if you advance to the next. So this is the first step that we want to take. We want to take something like what is on the left, a grayscale image, and do binarization. And then it's after that that you would do colorization. So if you could go to the next. And so we use a deep neural network-based approach here where we did learn the mapping from an original non-binary image, so a grayscale to a binary image. Now, typically, you would need thousands of images for something like this, but it turned out, only had 35 vascular images. So what we ended up doing is taking a bunch of image patches from images like what you see on the left, and therefore turning these into thousands of images. So if you could advance to the next. And so this is kind of an initial depiction of the kinds of accuracies we're getting. Certainly the numbers look pretty high, but it turns out there is still some need for improvement because there are some systematic errors. So we do tend to have essentially false positives, so showing additional vascular structure beyond what is really there, closer to the roots. And we tend to miss some of the smaller capillaries that you see, like in this case, towards the right side of the image. And also, we do need to take into account the fact that these different vessels are actually all connected. So that still needs to be taken into account. Also, we're working right now with 2D images. The vascular structure actually is three-dimensional. So we do hope to be able to work on dealing with this as a 3D problem in the fullness of time. So if you could go to the next. So that's just kind of a description of some of the problems. This is just describing this site called Dashlink. You see the URL for that. This is a place where you can look at information on different projects. This is mostly oriented towards data mining and systems health management, so probably mostly aviation, but some on the space side as well, where this is a community where people can share papers, open source algorithms, like the algorithms that we've developed are open source and we make them available on Dashlink. Some NASA relevant data sets are also available there. If you can see a lot without actually having an account there, but if you like, you can also sign up for an account on this. I will be the person who would have to approve membership. So if you do want to sign up and you mention this talk, I can approve your membership. And if you go to the next, I think actually that's the extent of what I'd planned to say.
Thank you so much,
please.
Nikunj. So we have a bunch of questions that have been waiting, so I'll read out, and then everybody else, please do put your questions on the Q&A, and I'll read them out for the speaker. So the first question is about, are state-of-the-art algorithms like neural networks used? So could you comment on kind of how much you guys use deep learning in your various projects?
So certainly where we have a large enough amount of data to be able to work with, or in cases like with the vascular images where we're able to, let's say where you have relatively few images in terms of, say, numbers of astronauts, but where we're able to make many image patches, we do make use of deep neural networks. but we do tend to use other algorithms as well. So, for example, for precursor identification, an initial algorithm that we developed was based on reinforcement learning and inverse reinforcement learning. Also, so far for the Kepler and TESS for the planet candidate identification, we have mostly been using. I know boosting was probably the one that produced the best results overall, so we ended up using that.
I see. Thank you. Appreciate that. And then I think the next question is, do you think that more the data-driven methods could one day replace the rule-based methods if once you have enough data?
I think really, I mean, it does depend on the domain, but in general, I have my doubts about actually being able to do a full-blown replacement. Because with because even the data that we get, I mean, they do have some problems with them, right? So, for example, with let's say with something like earth science data, remote sensing, the data start off as essentially, I mean, the raw data are essentially information on photons, and then they are transformed through multiple levels. So satellites, for example, move around the Earth in swaths, kind of like the way a yarn is wound around a ball. And so then the lower level data are essentially in those swaths. Then the data are stitched together. So the typical views of the full Earth that you see are data stitched together from different times. So, you know, that has its share of problems. So I think that there will always be a place, you know, for just some, in some cases, rule-based methods, but in some cases, even more complicated process models. So there are models, for example, for climate that are essentially systems of differential equations. So I think that there will still be a place for those. Maybe the data can help refine the models. In fact, I know within aviation, there's a fairly big community that takes different existing mathematical models and uses data to try and modify those models directly. And that actually is more informative to people in the domain, because these domain experts, they know the mathematical models so well that when they see a change in a coefficient for a particular term, they can right away realize that, okay, a certain phenomenon that they thought had moderate importance actually has more importance or has less importance or whatever it may be. So I feel like it's always going to be a team effort between domain experts and the kinds of models they construct, whether it's rule-based or mathematical models, and data.
Makes sense. Yeah, absolutely. So, and then I think there's a question about the approximate volume of data used. Are we talking gigabytes or terabytes? You guys have a ton of data and probably more every day.
Yeah, it really does vary by the domain. So we have anything like the you know, what I described about the vascular structure, where it's like 35 images that are, you know, each maybe, you know, tens of megs or hundreds of megs, all the way up to our earth science data, where I think right now, I think we're up to something like 5 petabytes. And I think the rate at which we get data is something like 10 terabytes a day. And there are plans to put instruments online that are going to generate that much just by themselves every day. So it really varies quite a bit over the different domains that we cover.
Makes sense. And then I think, you know, one of our students would like to actually answer a question that was asked. So Shivansh, so the question is, how do the kernels create the similarity? So Shivansh, is there something that you would like to say about this before Dr. Oza speaks to it? You can unmute Shivansh and speak. Shivansh, is there anything that you'd like to add? Maybe not, and maybe it was a mistake. So the question, Dr. Oza, is how do the kernels create the similarity?
Oh yes, so it's essentially a mathematical formula. So, for example, one measure that you can imagine using is actually just something like a Euclidean distance. One that we have used a fair amount is actually a Gaussian similarity. So in this case, it's taking, let's say you have the two different data points, you actually take the squared difference between them, the negative of that, and then take the exponential. And so that a 0, 1 space. So sorry, actually after doing all that, you actually before taking the exponential, you divide by the standard deviation. So that ends up mapping you into a 0, 1 space. There are also other kernel functions that are available. So yeah, many of them have been devised. And so there are, yeah, you'll probably see them in different papers describing things like, let's say, Gaussian processes. That's an example of a kernel method. Support vector machines. That's also a kernel method. Like, and in fact, one class support vector machines is what we used in the work that you're referring to. So different kernel functions are used. It's just essentially some way of saying how similar are these two data points. And you just have to make sure that if two data points are maximally similar, then the kernel function should map to 1. Whereas if the two data points are very different, then that should map to 0.
Makes sense. And I think, there's questions about, so does bad data happen due to sensor malfunction?
Oh God, bad data happens for many reasons. So certainly sensor malfunction is a possibility. Sometimes there are data recording issues. So in fact, there was one partner we worked with where they were supposed to collect some flight data, but they think somebody may have accidentally kicked the unit that was collecting data and ended up kicking the off switch. Sometimes you get it's not, sometimes you just get noise that is a function of the environment. So like I know I think one of my first projects, there was a vibration sensor, so essentially an accelerometer, but the error would go up as the ambient heat would go up. So a particular sensor that was too close to the engine was giving unreliable readings because it turned out the environment around the sensor was getting too hot. And then sometimes we get anomalies, kind of like I alluded to before, where you see what looks like a funny flight trajectory, but it turns out that air traffic control actually directed that aircraft to take a different trajectory. There was another one actually just happened last week or the week before that was really annoying, where we thought for an aircraft, the flap setting was kind of unusual, but it turned out for the sake of uniformity, they decided to have one column for flap setting for every aircraft type that the fleet had. And the only column that was valid was the column for that particular aircraft type. So it turned out we were looking at data from an A320, but somehow our algorithm was looking at the flap setting for an A321. And so that A321 flap data had junk in it, but it turned out that it was almost random data.
Wow.
So yeah, so you get like every kind of thing you can imagine with regard to quote bad data.
No, thank you so much. I think there are more questions, but I think we're a little out of time. But thank you so much, Dr. Oza. This is a wonderful presentation, and I think there were so many questions. There are a few questions on the chat that I think I will forward to you separately. And we also had one individual who tried to sign up at the site, at the dashboard.
Wow, that was quick.
And had an error. So I will offline send that error to you. And
thank you. Yes, that's actually a surprising problem as well that we run into with regard to data, right? People tell us data is a certain place, and it turned out it isn't, and so.
Yeah, but thank you so much. I will follow up. We have a bunch of things on the chat. I'll follow up with you and try to connect, the dots with the people who want to ask you various questions.
Yeah, absolutely. Yeah, thank you all.